Today we'll talk about regular polygon area, which we'll find is an application of triangle area, but quite a bit of work has to be done to get from the triangle area formula to the area of a particular polygon. So that's what we do today. Now, I'm about to define some terms for you, terms that you'll need to know. I'll use them all throughout, and I will mention some results that have to do with these terms. That we won't actually take the time to prove these results here. I'll just say a very little bit about how it could be done. I don't think you'll be surprised when I say to you that ultimately it's just triangle congruence that proves all of these results. All right, so let's say we have a regular polygon like the one you see in front of you. This is a regular hexagon, not that it particularly matters how many sides we've got. For every regular polygon, there is a point in its interior that is equidistant from the vertices. This point is called the center of the regular polygon, and each segment from a center out to a vertex is a circumradius. So in the regular hexagon you see in front of you, the center point is C. Notice that I have marked the distance from that center point out to each vertex. Those are the dashed segments, each of which has a single hash mark on it. So we have said that they are equal in length. And these segments are called circumradii. Apothum. This is the other term that I need to define for you, the final term. An apothum is a segment that goes from the center, and we know what that is, out to a side perpendicular to that side. So in the diagram that we have, once again, C is the center, and then we have a segment that goes from the center out perpendicular to a side, marked with the A, little a for apothum. Um, and in just a moment, we will define, or derive, I should say, an area formula in terms of the apothum. All right, so some properties of these terms that I have defined, and then we'll hop into the derivation of the area formula for regular polygons. The first of the properties is this, is that all apothums are equal in length. So look at the diagram. Perhaps I'll draw just a little bit here for you to help out so we can have a label. Let the center be represented by the C, and then the apothums are all the segments that go out from that center to a side perpendicular to it. So here we have an apothum number one, and apothum number two, and so on all the way around. I mean to say that these are all equal in length. Of course, that would be triangle congruence followed by CPCTE. And the second property of apothums is this, is that each bisects a side. So if you follow, for instance, the A1 apothum out to its side, notice that that side is split into two parts that are equal to one another. If you follow out the A2 apothum to its side, that side is split into two equal parts. And once again, no surprise here, this would ultimately be an application of triangle congruence. We would prove triangles congruent, and then we would follow that with CPCTE, and then we would know that the sides have been split. All right, we need one other property, in this case a property of a circumradius, and then we'll do the derivation of the area formula for a regular polygon. The property here of a circumradius is this, is that each circumradius bisects an angle. Remember that a circumradius is a segment that goes from the center, here it is once again, the center point C. The circumradius goes from the center point out to a vertex, and that's what the dash segments do here. And I say to you that each circumradius bisects an angle, as is shown in the diagram. And once again, if one had to prove that this were the case, one would construct triangles, which of course you see here. One would prove them congruent, and then it would follow by CPCTE that we had angles equal, and so on. All right, so let's actually derive the regular polygon area formula. Now, in the area formula, ultimately, what we'll need to know is, and this is the kind of work that we'll do for particular examples in just a moment, we'll need to know the number of sides. We'll need to know the length of an apothum. We'll need to know a side length. And once we know these, we can get a perimeter. And once we have a perimeter, we can get the area formula. So let me show you how this goes. All right, so like I said a moment ago at the start of this, that ultimately the regular polygon area formula is an application or an extension perhaps of the triangle area formula, because we decompose a regular polygon up into triangles, which is perhaps the most common kind of maneuver in this entire class. So let us take this regular hexagon with its apothum A, its side length S, and its number of sides N, which happens to be 6 in this case, but we'll work with just N. Let us take this regular hexagon, this regular polygon, and begin to carve it up into triangles. You see one in front of you. I'll talk about the rest in just a moment. Now let's think about the area of that triangle. So the area of that particular triangle, the one that I just created, is, of course, half base times height. That is the basic triangle area formula. In this case, it should be obvious that the base is S, the height is A. That's what an apothem does, doesn't it? It goes from a side out perpendicular to a vertex when we create the triangle. So the height is the A. So the area of the triangle is half SA. Now, how do we get the area of the regular polygon, which I will call just RP for regular polygon? Well, it should be clear that triangle is replicated multiple times. Now, of course, to make this fully rigorous, we would need to prove that these triangles are congruent to one another, and it would follow that because they are congruent, they have equal areas and so on. But that, I think, is fairly obvious, that all the triangles I've just created are equal in area. So all we have to do then is multiply the area of the triangle by the number of triangles that we now have, and that will be the area of the regular polygon. Well, how many do we have? Well, in the diagram in front of you, of course, it's 6. But we want a polygon area, regular polygon area formula that's perfectly general. So we'll just talk about a polygon, regular polygon with n sides, whatever that happens to be. Now it should be obvious that since the number of sides is n, the number of triangles will be n as well. So we have to take the area of the triangle and multiply it by n, and that will give the area of the regular polygon. But the area of the triangle is 1/2 SA, so that's n times 1/2 SA. And I want to rearrange this just a little bit so that it reaches its final form. So let me bring the n inside. So this is, of course, equal to 1/2 NSA. And I want you to think about that quantity n times s for just a moment. That's the number of sides times side length. And this, of course, is an irregular polygon where all the side lengths are equal to one another. So ask yourself, what is this quantity? What is another name for n times s? That, of course, is perimeter. So what we finally end up with is this, is that the area of a regular polygon is half of the perimeter times the apothem. And that's a very pretty little formula. And that's the one that we'll use in just a moment when we do a couple of problems. So here will be the strategy when we find the area of a particular given regular polygon. Well, you'll have the number of sides, you'll have to know that, and then you'll be given some length. That could be a side length, that could be an apothem, that could be a circumradius. Now here's what we'll do. We'll mark the center. Each regular polygon has one of those. We'll construct an apothem and a circumradius, and thereby create a right triangle. That will be the key to this procedure. And then we will use our knowledge of right triangles, which is both trig and the special right triangles, and perhaps the Pythagorean theorem as well, to find the values of P and A, that is perimeter and apothem. And we might know the apothem initially, but we might not, but we won't know both. So we'll have to do the work so that we have both. And then finally, we'll just plug into the A equals 1/2 PA formula. And then we'll have the area of the regular polygon. So let's do one. This is the kind of problem that you'll see on the assignment. I won't tell you the number of sides. You can count, of course. And then you'll do the construction that I just mentioned. You'll find values for P and A, and you'll get the area. So find the area of this regular hexagon. You can count the sides, 1, 2, 3, 4, 5, 6. So it's a hexagon, where the apothem has length 12. So here's the procedure. Mark the center. Okay, I'll call that C. From that center point, drop in an apothem. It doesn't matter the side to which you go. Easiest to go to the bottom, so I'll go there. So that's my apothem, which I know is 12. And then let me also construct a circumradius so that I end up with a right triangle. So there's a circumradius, which goes from the center to a vertex. Um, and then what we need is this. We have our area formula, right, which is 1/2 perimeter times apothem. Well, we've got the apothem, so what we need is the perimeter. And how will we get a perimeter? Well, to get a perimeter, we'll need to get a side length, right? So we'll need to get an entire side length. And the question is, how will we do that? Well, we're going to have to do work in the triangle that we created, which let's say is triangle ABC. So we can talk about it. Um, we'll have to do work inside of this triangle so that we can actually get the length of AB, which will be half a side length. So we can double that and get a side length. And once we know a side length, we can get the perimeter, and then we can get the area. So let's do the work necessary in this triangle to get the length of AB. Well, the only way that we can do this is to get an angle measure. This is part of the procedure. And this is the sort of thing that we've done before. How do you get an angle measure of a regular polygon? Well, so let's say an angle is theta. Here was the formula once again. It's the number of sides minus 2 times 180 degrees divided by the number of sides. I won't take the time to review why that is the correct formula. And let's plug in here. So we have 6 minus 2 times 180 degrees over 6, which is 4 times 180 degrees over 6, which is, if you do the math, 120 degrees. So every angle of this regular hexagon is 120 degrees. Now consider the segment CA. CA is a circumradius, so it bisects the angle A. That total angle at A is 120 degrees, and since it gets bisected, that means, of course, that we have 60 degrees. So notice what's happened here. This triangle, ABC, is a 30, 60, 90, which should allow me to get the length of AB. Well, let's think about that for just a moment. This is something that you're supposed to know, that is the side relationships in a 30, 60, 90. So I have here a 30, 60, 90, and the longer of the two legs, that is the leg opposite the 60-degree angle, is 12. That means the shorter of the two legs, which is AB, is that 12 divided by root 3. And let us go ahead and rationalize that because it will be much easier to work with. And the way that's rationalized is we multiply top and bottom by root 3. So we end up with 12 root 3 over root 3 times root 3 is 3, of course. 12 over 3 is 4. So this is 4 root 3. So AB is 4 root 3. That means that the side length is double that because each apothem bisects the side length. So a side length is 8 root 3. That means the total perimeter is 6 times 8 root 3, which is 48 root 3. And then finally, the area is half perimeter times apothem. So that's half perimeter, which is half of 48 root 3, times the apothem, which was 12. So that'll be 6 times 48. I think that's 288 root 3. So that's the area. And in this particular case, since we did end up with a 30, 60, 90 right triangle, we were able to get an exact expression for the area. And that's how your homework will be structured as well. Some problems will allow you to find exact expressions for the area, some will not. The ones where you can get exact values are, given the trig that we know, are squares, that is regular four-sided polygons, triangles as well, that is regular three-sided polygons, and regular six-sided polygons, that is hexagons. All right, so let's look at an example where we wouldn't be able to get an exact expression. That will involve trigonometry. All right, so here is a regular pentagon where R is 1, and R represents a circumradius. That is a segment from center out to a vertex. So procedure initially is the same. So let us mark the center point. Let us drop an apothem whose length we do not know. Let us also construct in a circumradius whose length we do know. And then, once again, we'll use the formula half perimeter times apothem. Well, in this case, we do not know perimeter, we do not know apothem, so we have to find both of these quantities. And again, this will require that we do work inside of the triangle that I created, which I'll call once again triangle ABC. And to do work inside of this triangle, to find out unknown side lengths in it, which is what we need, we have to get angle measures. So let us get an angle measure. So once again, if theta represents the measure of one of the angles, its measure will be the number of sides minus 2 times 180 degrees divided by the number of sides, and you can do the work here. That turns out to be 108 degrees. So every angle of the regular pentagon is 108 degrees. The segment CB, that is the circumradius, bisects angle B. So the angle of the triangle, angle CBA, is 54 degrees. And of course, we could find the measure of C as well, but we just won't need to do that, so we won't. All right, so let's get the length of the apothem, which is AC. Okay. Well, let's think about that. So there's AC. We wish to get the length of that particular segment. Well, relative to the 54-degree angle, that's the opposite leg, and one is the hypotenuse, of course. So we need the trig function that involves opposite and hypotenuse, and that's sine. So here's what we can say. We can say that the sine of 54 degrees is AC, which will be the apothem. So I'm going to call that little a, okay, over 1, and a over 1 is just a, so a is the sine of 54 degrees. So we've got some of our work done. We've got the length of the apothem. Now we need to get the length of the perimeter. And to do that, we need the length of AB. That is the base of our triangle because that's half a side length. And if we know then AB, we can find the total side length, which means that we can get the perimeter. And here, since we need to find AB, there it is, AB, this is adjacent to the 54-degree angle. And then, of course, we use the hypotenuse, which is 1. And that now is cosine. Cosine is adjacent over hypotenuse. So we have the cosine of 54 degrees is equal to AB. I'll just call this AB over 1, which of course is just AB. And then we can now get the perimeter because what do we do? Oops. What do we do to get the perimeter, given that we know AB? Well, we have to double it, and then we have to multiply it by 5. We double it to get one side length, but we have 5 total sides, so we double and then multiply by 5, which means we really multiply by 10. So P is 10 times AB, which will be 10 times the cosine of 54 degrees. And then we can all put this together. And notice that I haven't yet begun to approximate anything. I like to do it like this so I don't have to drag around the decimal point if I need to approximate. And I will in this case, I will do that at the very end. So let's see, what is the area? The area is half BA. So perimeter turned out to be 10 times the cosine of 54 degrees. And A turned out to be the sine of 54 degrees. So just a little bit of simplification before we approximate. Half of 10 is 5. So this is 5 times the cosine of 54 degrees times the sine of 54 degrees. Now at this point I think I'll stop. You can either go to your table or to a calculator and get approximate values for the cosine of 54 and the sine of 54, and then plug those on and you'll get your area. Now, as for how you'll actually verify that the work you do on today's assignment is correct, well, I didn't put any answers in the solutions file. And the reason I didn't do that is because I didn't need to do that, because you have available to you this online tool called Wolfram Alpha that will answer your questions for you. So you can go to Wolfram Alpha, and then once you're there, you can go to the query bar, the question bar, and you can type in expressions like the one you see. Area regular sixgon, apothem 12. You could call that hexagon if you like, but if you forget the name of a particular insided polygon, you can just use the number / gon. And then the Wolfram Alpha will tell you the result. It will give you an exact value if it can do that, and it will also give you an approximation. So for each of the problems that you do, to verify that your work is correct, just hop over to Wolfram Alpha, type it in, and you'll get the correct answer. And it's good for you to know about the existence of Wolfram Alpha. It is an extremely powerful tool. I use it regularly. Often if there's, for instance, some algebra that I need to verify, or simply that I don't want to do that I know how to do, but I don't want to take the time to do it, I'll let Wolfram Alpha do the work for me. You should know that it exists. Of course, you need to be able to do the work yourself, but it is wonderful to work with to verify that your answers are correct.